Hello, everyone. This is Mike Mazzarese with AST Environmental. Good morning, good afternoon, or good evening, I guess, depending on where you're joining us from today. We have some folks here still signing in, so we'll get through some housekeeping before I hand it over to Bill. And so this is, we've been rolling out these sort of platform presentation style webinars in 2021. So we're going to follow with that next month. We're going to highlight the CAT 100 technology. So that's for chlorinated solvents, specifically for higher concentration sites. And so we're going to talk about all the projects to date where we've used that technology over the last 4 or 5 years. So we haven't posted the date or the time for that yet, but that'll be in about a month from now, next month. So keep an eye out for that email from us. If you have to jump off early, we understand you're all busy. If you have to jump off early, this will be recorded, or it's being recorded, excuse me, and will be on our website within the next week. So if you go to astenv.com, go to the upper right-hand corner, you'll see a link for webinars. Just click on that, and we're in chronological order with the most recent at the top. Okay. Lastly, I know everyone here, I'm sure you're all pros at this point. Submit your questions there in your tab to the right. And we'll be fielding those for the last 5-10 minutes here of the webinar. If we can't get to them, we're going to try to hold this at 40 minutes. If we can't get to them, either Bill or myself will follow up with you. And okay, well, we'll go ahead and get started here. So Bill Brab, senior remediation geologist with AST Environmental, based in Kentucky, here in the United States. And Bill has he's done quite a few of these webinars for us. If you have, in particular, any bedrock applications, Bill's done an excellent job on. We've done multiple webinars on bedrock characterization as well as remediation, so I recommend you check those out on our website. Today, however, we aren't covering bedrock. We'll be covering a BOS 200 application at an LNAPL site that had a pipeline transmission rupture. So, Bill, I'll go ahead and hand it over to you.
Thank you for the introduction, Mike. Can you hear me okay? Sound coming through clearly?
Yes.
Great. All right. So we'll go live here. Everybody, thanks for attending. I know folks are probably weary of the routine of webinars and such, but we definitely appreciate your time. Things are starting to open up for everybody a little bit for being out and doing things in public again. So again, your time is quite valuable to us, and we really appreciate you coming on to hear what we have to say today. So without further ado, I'll move forward. Mike's already covered the title topic here. So a little bit of background on the site, looking specifically at the details of the facility, where it's located. Geologically, it's located in the Thumb Upland Physiographic Region of Michigan's Lower Peninsula. And the overburden is predominantly a sand and gravel unit, varying in thickness from anywhere from 8 foot to 22 foot, depending on where you are in the facility. Consolidated material directly beneath that is a sandstone and shale unit coming from the Saginaw Formation. And your groundwater occurs at the site roughly from 9 foot to 14 foot below grade, primarily in the unconsolidated sediment aquifer. There is a bedrock aquifer directly beneath in the consolidated unit. And that groundwater analytical data from historical sampling indicates that there's a hydraulic connection between those two units, as we'll see in some subsequent slides. The pipeline facility itself is located in southern Michigan. The release that Mike talked about in the introduction was comprised of a 1,700 barrel release of gasoline in 2000, resulting from the failure of a 16-inch stopple fitting within the transmission facility. During the recovery efforts and mitigation of that release, approximately 1,400 barrels were estimated to be recovered during the initial response. Subsequent mitigation activities included the excavation and removal of approximately 30,000 tons of impacted soil for off-site disposal. There was a groundwater extraction system operated on the site capable of about 25,000 gallons per month. That was operated until about 2012. Quarterly monitoring was conducted all the way up until not present, but June of 2019, as we'll see in subsequent slides. Looking at the conceptual site model in the first quarter of 2013, when AST first became involved, looking specifically at the full conceptual site model, sampling of that media indicated sorbed mass was located roughly 4 to 5 foot below grade and extended below the water table. This was indicated through the use of PID readings in the saturated soil, but as is similar to some sampling protocols in different regions of the U.S. and abroad, sampling of saturated soil below the water table was not directed or is not accepted protocol in some instances for compliance testing. The groundwater model, however, is a little bit different than the soil models we can see here based on the more extensive sampling involved. We do have an elongated plume looking specifically on the project facility, which is located, one second, get my pointer here. So we got the laser pointer on the screen. This is the transmission facility here on the bottom left-hand corner of the graphical figure that we see. The release within that stopple fitting occurred within this transfer rack here, or metering rack located within the facility. This is the fence line demarcating the edge of that meter station itself. We do have a LNAPL extensive on-site within the source area here. That material spilled and discharged down along this perennial stream directly adjacent to the railway. And we have essentially persistent LNAPL is located within that overburden area within the source with low-level dissolve phase, as we indicated before, that the overburden and the shallow bedrock were in fact connected hydraulically. If we look at this map here, this monitoring well 24D, located about 380 foot down gradient, is actually located within that shallow bedrock aquifer. And there were some low-level impacts of hydrocarbons within that zone. So at the time that AST became involved, some remedial objectives that were set forth that we were working with both MDEQ and our client, as well as the RP involved here, were kind of set forth at the initial stages of review and evaluation. No soil goal was specified at the time of initial consultation, but however, they did want to see a significant reduction in the groundwater contaminants of concern, as well as an elimination of measurable NAPL within that source area located directly down gradient from the actual meter station itself. We were contacted in early 2013 to provide a remedial option, and that consisted of a preliminary injection design based on the existing CSM, which we just saw above for budgeting purposes. Through the identification of data gaps, we came up with remedial design characterization to get some additional sampling to fill that in. We'll talk about that shortly. And for the preliminary budgeting for the remediation, a pilot scale injection using BOS 200 and follow up with a full scale injection to manage the additional masses outside of that pilot area. And so if you've seen presentations by AST and RPI, you've no doubt seen this roadmap here to success, which is just generically called the approach. And essentially what we're going through here is just a process of walking through the stages of initial review, data gap filling through the RDC, where we try and get some higher resolution and better indications of distribution of mass and quantification, coming back to the table and looking at that conceptual site model and refining it based upon that data, and then actually going out into the field and implementing whatever technology is applicable to that specific site and contaminant stream that we're trying to deal with. And then, of course, at the end, we don't just walk away. We want to monitor it and make sure that what we expect to see is actually occurring, and if there's any adjustments that need to be made as we walk through the evaluation and monitoring of the site over time. So talking about the technologies involved here, I mentioned earlier that we were targeting this site at the time to utilize BOS 200. The trap and treat products obviously include some other materials that are geared towards different contaminants based on what site you're dealing with. This site at the time of assessment and implementation was during the early stages prior to BOS 200 Plus being introduced. And BOS 200, if you're not familiar with that, is a powdered activated carbon for petroleum hydrocarbons remediation. And that powdered activated carbon is mixed with terminal electron acceptors in the form typically of sulfate and nitrate. We add some macro and micronutrients to that, and then add a facultative blend consortium of bacteria for the purpose of regenerating that carbon in situ over time through biological degradation of that contaminant. So looking at the RDC for this specific site, the remedial design characterization. So here we can see on the site figure, the transmission facility is located here. Coming out of the transmission facility, we have a series of pipelines that run in this direction, and one crosses over here and goes kind of off to the left of the map here. Your purple points on the figure here are your individual RDC points. And if we look at the detail on the far right in the bullets, the RDC consisted of 34 soil borings installed to the top of bedrock. Those samples were continuously screened for every 2 foot and submitted for laboratory analysis. Laboratory analysis at RPI's lab in Golden, Colorado provides the pro bono analytical for us to utilize to obtain this high level of data density that we need for these sites. Those analyses included speciated BOCs constituents, as well as looking at that total volatile hydrocarbon mass fraction to be able to look at the total mass present within the system. At each of those 34 soil borings, we also installed 34 nested well pairs in the completed borings. These are for discrete intervals looking at vertical delineation of that groundwater concentration with depth. There was a deep interval that was installed essentially from top of bedrock to about 4 foot above rock. And then we installed a shallow interval that was separated by a bentonite seal so that we could see if there was a concentration gradient across that vertical horizon. Those samples were also analyzed for VOCs, which included that TDPH as well as anion to look at background concentrations of those. And again, as I mentioned before, RPI provides this analysis free of charge for any project that we're involved in. And so looking at that RDC, moving forward with updating the conceptual model, at the time of coming back to the table to talk about this, soil standard was in fact defined by MDEQ on this site of 10 ppb benzene in soil, and looking at that MCL for the groundwater benzene concentration. And so the figure on your left-hand side here, we just want to reference this to kind of talk back to looking at the benefits of the RDC. We can see the pipelines again, and then these purple areas are going to reference the pilot scale area versus the full-scale design that was provided as part of the initial review, looking at the existing data. And so the benefits of the RDC that came about this really shed some very valuable information for gauging performance and expectations moving forward from initial review into actual field scale implementation. So the preliminary conceptual site model compared to the RDC data showed that there was an underestimation of treatment mass in that pilot scale area of about 20% shy of what we needed. So not very significant there, but when we actually looked at the second event on the full scale, the available data versus what we found from the RDC showed that we wouldn't have even come close to being able to address that contaminant mass present within the site. Very contaminated, highly contaminated site. There was significant soil mass that was present across the unsaturated and saturated intervals within that soil media, and that contribution to the actual total contaminant mass of site was actually coming from that saturated zone within the soil zone. So that RDC also allowed us to come into play with a more surgical approach where we could vary the loadings of the BOS 200 with depth based on the actual mass located within a specific area and its distribution across that zone. And so just to give you a little bit of example of some of the data that was obtained from the RDC, we're looking at 2 soil borings here initiated within the source area itself, RDC 11, RDC 12. If you look at the plots here on the left and right, they're essentially mirrors of one another, the blue line being benzene, the orange line being TDPH from soil, the dots on those respected to the individual sample depth interval that we sampled from, water tables depicted, and then you can see the bars on the left-hand side of each of these plots are showing the screened interval for the discrete interval samples that we put in on the nested well pair. So you see your shallow and deep zone. And so again, as what we can see from typical, or at least from the historical sampling, with your RDC 11 sample, you do have a fairly significant amount of mass just above the water table, and that's reflected by the groundwater sample that's shown from that shallow interval. But we can see in both of these, it's very important to pull out is that there is significant contaminant mass that is actually below the water table. And when you're actually trying to quantify and define the amount of mass present at the site and how to address it, if you don't have this information, you're underestimating your total mass and likely your treatment interval that needs to be addressed. So some of this data here is pretty important to be able to design around properly. And as we can see from the map on the left-hand side here again, we have that overlay of the purple lines that are showing the preliminary conceptual model that expands beyond the area that was actually applied for the actual revised design as we see here. The right-hand side is quite busy, but the importance to look at on the right-hand side is how we carved this site up, how we define these zones to reflect the individual concentrations and intervals that were identified during the RDC. And so on the left-hand side, looking at that figure again, if we look at areas A through K, you can clearly see that those are identified on that figure, and the level of detail and segregation, so to speak, across the zone of interest that we've targeted for this treatment. As part of that preliminary or follow-up conceptual model and redesign, we've targeted the site for 2 injection events. However, we did deploy a 3rd injection event out here, which we'll show highlighted on a future slide. And so we also can't forget the importance of actually implementing the technology, right? So we have a great front-end investigation to identify and quantify contaminant mass. We have a very good picture of that distribution. But then the other thing we have is an excellent product that essentially is very powerful for removing mass from the system and treating that contaminant in place. But then the other part of that that's very important is actually installing the material in the proper way. So, you know, looking at installation of slurries, we're not pumping a solution in, we're not trying to occupy pore volume, we're actually installing a solid particle to become part of the aquifer matrix. And so these slurries are implemented under a high flow rate and relatively small injection volumes across each individual point. Our grid spacing out here was on a 5-foot grid spacing during the 1st and 2nd event. We went to as small as a 3-foot grid spacing on the 3rd injection event. We place this material in the formation. We do that in a top-down manner where the path of least resistance is in the horizontal versus the vertical. And these are dedicated temporary points. And the other part to see here that's important is that we orient our injection point rows perpendicular to groundwater flow for the purpose of providing some level of intercept for seep coming out of that area of contamination. And then finally, looking at the left-hand side, we can see from this injection method here, we've got a completed point here that's backfilled with bentonite to seal that borehole to prevent any sort of daylighting coming back or path of least resistance into that borehole. And adjacent points are going to be offset by roughly 1 foot so that we get an overlap of those intervals as we're moving both left to right on the rows within this particular row. But if we're going into and out of the page on your screen, you can see this in 3 dimensions as well. So we get this 3-dimensional lattice work of interconnected zones of injection. And so this is just a photographic view of the site prior to the 1st injection event completed in April 2014. We're looking north here at the site. Here's the transmission facility on the left-hand side. This is that rack I mentioned here where the stoppel fitting failed and where the release actually occurred. And that material released and discharged down across the site here and kind of followed this roadway that we see off to the right-hand side. ASD injection unit in the background, and here's the BOS 200 delivered to the site itself. And then your markers here denote the location of the transmission lines as they're leaving the facility. So following the 1st injection event, about 1 year after that, we came back to the site and did some limited soil sampling and investigation as a 2nd RDC. This was planned from day 1 to be able to, first of all, look for the distribution of BOS 200 within the samples that we pulled from. But the idea was also to get current data prior to going in on the 2nd event to establish a new baseline. So this was completed adjacent to the key locations, about 12 locations adjacent to the 2013 RDC that was completed prior to the 1st event. We did collect some groundwater sample grabs from those locations as well, just to see what the groundwater reflection of that soil mass was. And again, we looked for the presence of BOS 200. Lab analysis, again, was performed pro bono for the purpose of establishing that second baseline prior to the second event. We could estimate it based upon that limited soil data set and groundwater data set, some level of degradation rate following the first injection event. And so looking at just that data set alone, we had reductions in soil of up to about 85% in benzene, as well as 68% of reduction in TDPH in some areas, in some samples. Groundwater mass reductions, similarly, were around 73% for benzene, 88% reductions in TDPH. The full-scale BOS 200 event was approved and implemented following this RDC in April 2016, and then a third event in the source area was also approved for coming back in August 2018 to further bolster the installation that had been done in 2014. And so back to these graphical representations of the data. This is taking that second round of RDC data, comparing it to the first. This slide here, we're looking specifically at RDC 11. So we're back in the source area, looking at the soil sample directly adjacent to a pipeline, one of the pipelines coming out of the facility. And so the graph on the left-hand side shows benzene, TDPH on the right-hand side as well. And I've overlaid both the water table and injection interval. And so what we can see here that's quite striking and important again is looking at that, this is outside of the treatment interval. So anything above 4 feet did not receive treatment, which we see no reduction there in benzene. But then once we get down, we can see the differences in contaminant reduction based upon where we're at in either saturated or unsaturated media. The reduction in contaminant mass in the unsaturated zone is a little bit slower, but here we got some good distribution, it looks like, and we got a big knockdown in benzene, and that shows that it continues down into the saturated zone and removal of mass down below the water table. Looking at the TDPH, we've got a little variation in the sample data on the TDPH, but we can see the benzene's performing quite well, which is the regulated compound. But we do see great reductions in the TDPH in all of their samples collected. Moving forward to RDC 12, which is adjacent to that on the same row of samples that we collected. Similar results here. The benzene data looks fantastic, looking at that high concentration mass of both TDPH and benzene below the water table. Again, we're looking at that similar concentration, no change above the injection interval. And looking at that TDPH, again, we got that kind of weird anomaly right there at the water table, just due to the sampling variability coming back and trying to replicate that sample. So now we're looking at groundwater data from RDC 12D. This is looking at the deeper groundwater sample interval that's put in out here. What we just want to highlight here is the response of both contaminant concentration and the addition of the terminal electron acceptor. So what we see here on the graph is looking at injection event 1 located here, injection event 2 located here, and third injection event located here in 2018. And essentially what we're seeing here is the benzene high concentration initially with the striking drop due to the introduction of the carbon. So we're looking at the trap component, the new equilibrium of benzene following that injection. And then as the biological process kicks off, we see that rate of reduction. And again, we see this replicated in each injection event. We'll see a high concentration prior, and then a new equilibrium established right after that. A little variability here, but again, we're back down to that lower concentration. And then the mirror image of that is the addition of the sulfate. So we're down at 0. We're adding sulfate to the system, and it's being consumed in parallel to the benzene. Spike again, consumed in parallel, spike again, consumed in parallel. So just a nice visual representation of how to look at this data when it's coming back to you after we've worked on one of these sites. And so the really great thing about this facility is that we've got many years of data, great field scale implementation here to demonstrate the effectiveness of the technology. And so if we look here at this particular, we're going to walk through a series of contaminant concentration maps on the left-hand side, followed by a simple calculation looking strictly at groundwater for the calculation of mass reduction within that media over time. And so you may remember this particular figure from earlier. This is at time equals 0, groundwater sampling prior to the first injection event in 2014. We can see that NAPL here located within the central zone and the elongated plume with low-level triple-digit concentration ppb of benzene in that shallow bedrock well, NW24D up on the right-hand side. And we'll summarize all this at the end, but just note the number here on the right-hand side. We're looking at pounds of benzene, roughly 5.9 pounds of benzene located within this specific area. And so as we kind of start walking forward in time, I just want you to kind of flip your eyes back and forth between the left image and the right image. And we want to see the scale and distribution of the mass as well as the quantification on the right-hand side to help us understand what's going on within this area. So we're looking at about 6 months post first injection event in December 2014 here. Got a significant knockdown in the total mass of benzene if we're looking at it on the calculated table to the right. The other thing we can see here is immediately we cut off the source of contamination being seen in that distal end down in that bedrock aquifer. And what's really nice about this is we see that does not return in any future slides that we have here in front of us. So now we're about 11 months coming up on the 1-year mark post-injection. We can see the geometry of the plume and the orientation of the hot spots is reorienting itself just adjacent to the transmission facility itself. Looking at that sampling event in June 2015 when we performed the second RDC out here, located, again, we can see from the right-hand side, we're continuing to see knockdown in contaminant mass as things continue to stabilize. Moving forward to about 1.5 years following the first injection event, a little bit of reorientation, some 100 ppb concentration showing up here as things reorient itself. But again, this was slated for multiple injection events, so it's going to reflect what we expect to see with things kind of changing as we move forward with time. Now we're looking at time equals 0 again, but this time we're right before the second injection event, which was completed in April of 2016. Looking at that geometry again, as well as that total mass calculation on the right-hand side, looking at the groundwater part. So now we move forward to about 11 months, almost the 1-year mark following the second injection event. That contamination and orientation of the occurrences of LNAPL is showing up closer and closer to that property line. Moving forward to June 2017, we do have a cyclical appearance of LNAPL at the site that typically shows up in the later months, November, December of the sampling years. So here we have that little blip of LNAPL showing up where the pipelines cross there in the NW26R. Again, that mass on the right-hand side continuing to fall, continuing to decrease as we go with time. Looking at March 2018, so we're roughly 4 years post first injection event. 5 years, or excuse me, another quarter after that. Again, we see that little blip of LNAPL showing up where the pipelines cross. So now we're looking at a baseline sampling event prior to the third and final injection event completed out here, down to about a little bit less than half a pound of benzene left based on calculation of mass out here. Now we're at just before that third event located, it's right after the event post-injection. So we can see, really cool slide here, we can see the power of that carbon absorption and direct mass removal system. Everything is now sucked back in and located within the source area between the pipelines. See a little bit of readjustment getting into that fall area where we see that LNAPL wanting to pop up as just a minor sheen on some of these monitoring wells and nesting sets that we have out here. March 2019, things have stabilized. Now we're at just some higher concentration zone located within that source area where 12R and 11 is located. Looking at June 2019, the decision has been made to decrease the sampling interval to semi-annual. Now looking at December 19, again, just those little blips showing up in the scene of LNAPL there, right where the pipelines are crossing and located. Keep in mind, we can't inject around the pipeline, so we do have a sustained source both coming out of the meter station and out of the backfill around these pipelines that are leaving the facility that we have to manage with time. So again, that LNAPL is kind of just located there on the right-hand side. Again, it's just a minor sheen showing up intermittently from time to time. And then looking at the final sampling event that's available to us as of right now, in December 2020 of last year, we can just see that everything is pretty much right into the property boundaries of the transmission facility itself. Again, we just see that little bit of sheen showing up right adjacent to that pipeline as it's coming out. If you remember from earlier, you have a pipeline discharging here and another one discharging here in parallel, and they cross right here. So you kind of have a little bit of a hydraulic trap that I think is part of the reason we're seeing some of that contamination showing up regularly within that specific area. And so now taking all of that information that I just presented to summarize for you, just to be very clear as to what we're seeing, using the groundwater as the indication for managing that contaminant mass on that specific area of the site. Looking at an initial total mass in April 2014, looking at groundwater here specifically, not including the soil component, but looking at about 5.9 pounds of benzene in April 2014 compared to 0.45 pounds of benzene in December 2020 during the last event, which equates to a roughly 92% total reduction in mass based on the groundwater data present. There's just a nice visual representation of that data as well in graphical form to help you visualize that reduction with the 3 individual injection events shown on the screen. We can see that nice linear decay off to the right-hand side showing progress and removal of mass in the system. With that, I'm essentially right at the 30-minute mark. As Mike mentioned before, well, thank you for joining us, obviously. Appreciate you all taking the time to hear the discussion today and this presentation of this site, an actual case study of field implementation. Mike did mention that we have both an archive of our webinars that we put on, which includes overburden and bedrock applications, as well as different contaminant streams, whether it be petroleum hydrocarbon or the chlorine ethylene side of things. So that website or that web link is available for you up on the screen if you'd like to go to that and bookmark it for future reference. Also, my contact information is on the screen if you want to reach out to me directly for any of the information, follow up on this particular presentation or any of the ones that you've seen before that you may want to get more information and talk personally about. But with that, I'll transition to Mike, let him field any questions that we may have my way, and we'll take it from there.
Awesome. Thanks. Thanks, Bill. That was excellent. Thank you for, I know that was a lot to get through in 30 minutes. So there are some questions that are coming in. So I'll just go ahead and start fielding those. Again, we're gonna pretty much have a hard stop at 40 minutes in. So if we can't get to your questions, we'll follow up directly, but we'll go ahead and get those started. First question, Bill, how did you select your injection point spacing to ensure your radius of influence was sufficient?
Yeah, it's a great question. So the injection point spacing and interval, as well as the loadings, is dictated by many factors. One, of course, being the contaminant loading. We have to take that into consideration most definitely when looking at the reagent loading. But we also, when looking at injection spacing and vertical interval spacing, we have to take into account the contaminant. We have to take into account the geology and the depth of both groundwater and the depth of the injections. So this specific site here, again, we've selected a 5-foot grid on the first and second injection event because of the depth at which we were beginning injections at 4 feet, as well as the geology we were dealing with was primarily a sandier matrix. So we wanted to make sure we had an adequate spacing and injection volume to get the distribution horizontally that we wish to achieve at this particular facility. I think that answers the question, hopefully.
Yeah, no, I think that's a good summary. Second question, how was the initial 1,400 barrels recovered?
It was a combination of surface back services, so bringing in, a pump truck or whatnot to be able to recover material via vacuum ability on the surface, booms, pads, anything that would essentially capture that material and allow it for recollection. And then some of that estimation was also from the excavation itself, the 30,000 tons, looking at sumps and areas where they could collect that material. So I'd say there was probably some level of quantification that was accurate based on looking at that liquid fraction actually measured, graduated, versus what would be estimated based on, an estimation of what's present in the material that was used to sorb and hold that material for recovery.
Okay. Next question. What happens to the BOS 200 in the environment? Does it just persist after remediation, changing the aquifer conditions permanently?
Yeah, another great question. So as I mentioned, this material is installed as a solid particle, becomes part of the aquifer matrix. So BOS 200 is made from bituminous coal, activated carbon, and so it's a powdered material that, you know, think of flour or talcum powder, and that material again is applied under high flow rates to be in place and just become another grain of material within that aquifer matrix. So what happens is that material becomes in place and becomes a permanent fixture to the formation itself for being in both direct contact with the groundwater and providing that long-term protection over time. And as long as there's the components to continue with degradation, that material will work indefinitely until either there's depletion of material or mineralizes, which is a long time from now. So it becomes part of the matrix and persists over time. And as long as there's an ability to strip that material from the groundwater and provide regeneration, it's going to continue to work with time.
Right. Yeah. I'll just add one comment on there. And so when we work up these designs, we're designing it off of total mass, and so we're accounting for, you know, everything that's in sorbed and aqueous. So at the very end, theoretically, when all the hydrocarbons are degraded and your electron acceptors go back down to their background level, and on this site, Bill, if I recall, the sulfate concentration baseline was pretty much close to zero.
Yes.
Or it was pretty low. So once those go down, the, you know, degradation kinetics are going to slow down significantly, and the carbon will stay in place, and it's not going to significantly impact the geochemistry of the site. So, okay, so how close to the pipeline were you able to inject?
It varied based on when we did the initial install. So the initial first event, we were able to get within 5 feet of the line. However, there was a transition of management of the facility in future injection events where that distance was increased to 8 feet. Those were, I believe, 30-inch lines, so they were quite large and very sensitive to not get anywhere near them. So closest we could get was 5 feet during the initial injection event.
Okay. Thank you. All right, so we've got someone, I guess, that attended our webinar last month and is asking if this would have been a good candidate for QHRSC quantitative high-risk site characterization. For those of you that didn't attend that webinar last month, if it would be a good candidate for modeling.
Oh, absolutely. I think it would be an excellent candidate. Again, we're trying to always, with these investigations, the idea is to have the best image in our head, as well as an understanding of distribution of mass at the facility and the geology and hydrogeology, and the improvements that have been made to the RDC and the integration and introduction of the QHRSC program. I definitely think that you know, 2 improvements that would have been done here if this were to come to the plate today would be on the front end doing the QHRSC as part of the initial program, and probably using the BOS 200 Plus to further bolster that installed material and increase those rates of production even further.
Yeah, so we're kind of up against it time-wise, but if you're interested in that, that QHRSC basically integrates that RDC process that Bill mentioned with back-end 3D quantitative modeling. And so if you're interested, that webinar is on our website, or you can reach out to us. We can give you some more information on that. That's an excellent question. We are up against it. There's someone that wrote kind of a long question. The initials GB. I don't want to give the person's name out. I'm gonna forward this off to Bill because it's kind of a lengthy question and we're up against our time here. And Bill will reach out to you directly to go ahead and answer that. But other than that, we got through all the questions. I want to thank everyone for attending. I know you're attending more webinars these days than you ever have. So we very much appreciate your time, and we hope that you could join us in the future. Enjoy the rest of your day. Thank you. And thank you, Bill.
Thanks, everyone. Thanks, Mike.